Good afternoon, everybody. Thank you for taking some time out of your day to come to this talk. I know it's been a long day, but have you all enjoyed PDC this far? Cool. So my name is Joe Duffy. I'm a program manager on the Common Language Runtime team at Microsoft. My primary focus is on concurrency programming models, so I own the system threading namespace, some future directions there. I also do a lot of work on API design, making sure that we're good at documenting and helping other teams follow API design best practices within Microsoft. So this session is Fun 405, Programming with Concurrency Part 2. The basic set of topics we're going to cover are a set of very deep technical topics. We're going to be sort of taking a look at concurrency through an internals lens. So the primary takeaways here for you, hopefully, is to walk away thinking, gosh, I listened to Jan, and concurrency isn't that hard. But once you step outside of the bounds of simple locking mechanisms, there's a lot of things to think about. The architecture on Windows is a very deep, rich architecture that's evolved over time. And taking a look at that provides some insight into why Jan may have been providing some of the advice that he did in his talk. Actually, on that topic, how many of you actually just came from Jan's talk? Wow, that's like 99%. So did you enjoy it? Yes. Awesome. So I do have a little bit of content that will reinforce Jan's messages. Hopefully it won't be seen as duplication. It should be complementary, really to drive home the important messages in concurrency. So let's take a look at the agenda here. What we're first going to do is talk about shared memory. Jan introduced this concept to you. He talked about the different programming models that you can use when you're programming concurrency. Shared memory is the most prevalent, at least if you're doing programming on Windows and the CLR. Then we'll take a look through example of what it takes to actually implement a lock on the CLR. Now, it's not that most of you will actually go home and write a lock yourself, but through the process of looking at what it takes to write a lock, you can learn quite a bit about how the CLR works, how concurrency on the platform actually works. We'll then look at memory models, which is a very geeky, low-level topic, which should be interesting. And hopefully, if any of you are thinking about doing lock-free programming, this should guide you in the right direction, which is that of using locks, which Jan told you about. But it's still in the theme of understanding the architecture, giving some unique insight into concurrency. This is a great topic. And lastly, we'll look at GUIs and COM architectures. So GUI threads, things like that, how COM interacts with GUIs. You might think that they're completely disjoint and unrelated topics, but after that section, you'll understand why they're coupled together. So with that, let's get started with shared memory. So there's sort of two primary ways for code running in parallel to communicate with each other and to share data. Jan spoke briefly about message passing. If you went to the cluster computing talk, which I believe was this morning, you would have heard about MPI, which is message passing interface, which is the standardized way to pass messages. It's very much like Indigo, or Windows Communication Framework. However, when you're working on Windows in the CLR, by and large, you'll use shared memory to actually communicate between workers. So producer and consumer might share access to a queue on the heap, for example, and that's how one worker gives something to the other. So on Windows, multiple threads inside of a process actually share access to the same address space. On the CLR, this means you can actually share static variables across threads. It means that you can pass pointers to objects on the heap to other threads executing. And if you're writing native code, you can do a raw memory offset into the address space and maybe accidentally share data across threads. There is also the notion of machine-wide sharing. So processes can actually share access to memory through sort of virtual address spaces. Windows provides, for example, memory mapped I/O, which essentially is the same thing as sharing a heap within a process. But however, the memories actually can be accessed from multiple processes and the threads within them concurrently. And furthermore, Windows actually has kernel objects, which can be shared at a machine level as well. So as Jan talked about, with sharing comes responsibility. So you need to work to protect your invariants, avoid corruption. So as a quick example, consider if you used a list of T instance and you wanted to share access within one program to that. You might share it through a static variable. You might share it by passing it to the thread start constructors, for example, and then multiple threads could be accessing it. So consider what happens if they both attempt to add something to that list simultaneously. Well, thread A may call the add function. The first thing it will do is load the next item index onto its stack. So a list probably uses an array as a backing store, and it needs to know where to put the next item in that list. Now, say after thread A has done that, it's preempted, and thread B runs. It calls add on the same instance. It loads up the same value for the next item index, stores the item in the array, and then increments the index and returns. So at that point in time, thread B's item is actually in the array. Unfortunately, thread A might then resume, and it still has the old value on its stack for the next item index. So what's it going to do? Well, it's going to overwrite the value that was just stored by thread B. Now, that's not going to be an easy thing to debug either. Imagine the consequences. It's not going to be a crash, but what will happen is that an item that seemingly got added to the list successfully simply goes missing at some point. Worse things can happen. Lists dynamically grow if you reach the capacity. So you can imagine both threads contending for the same list. Both of them invoke the grow method. That involves a set of reads and writes, which can get interleaved in very unintuitive ways that you didn't expect when you wrote your code. That could result in a corrupt data structure. Now, corrupting a data structure across a single process is bad. The process might crash due to an unhandled exception, for example. But even worse is if you're sharing the data structure across a set of processes on a machine. Now, if the processes weren't written to recover from that type of situation, you could force the user to notice this corruption by the fact that your programs may not run. They may try to restart them, and the shared memory is still corrupt, and they may actually have to reboot the system to recover. This is obviously a bad situation. So again, what are invariants? Well, invariants are conditions that you assume to be true in your code. And there's a lot of assumptions you can make in sequential code that can be violated when run concurrently. For example, you may have methods that mutate a set of variables, and you have some relationship between them. And then you exit from the method, and they're always true. But unfortunately, when you share that data structure concurrently, two things can be in there at the same time and notice this inconsistency. So again, to reinforce Jan's message, locking is the simplest way to fix this. Serialization forces things to happen one after another. So this first block of code here is using the lock statement in C#, which you saw uses the monitor class. It can go and change the data structure however it likes, leave it in a good state before it exits, and then provided that everybody accessing that data structure does so through the locking protocol, you can be ensured that broken invariants won't be observed by other programs or other threads within your program. Atomicity is another sort of thing that you can achieve when using locks. So say that you might throw an exception. You may start an operation that increments a variable, and then you do something else, and then you have to do something, a paired operation with that first invariant that you broke to put the invariants back into place. If an exception occurs, well, if you haven't written a catch block or a finally block to make sure that things are okay before control transfers out of that block, well, you can end up actually leaving things in a corrupt state still. So this isn't something you get for free using locking. You actually have to be explicit by using try and catches in a fairly simple manner, as demonstrated by the second block, within your lock block. So now that you understand sort of some of the principles of locking, you might wonder, well, what guarantees do we make in the .NET framework, in the CLR? Are there situations where simply running code that we provide you concurrently will break? The good answer is that any of our algorithms, any of our classes that rely on shared state to work properly, so if you have a class that hides a static variable and its implementation accesses that static variable for some reason that you may not even care about, it's guaranteed to do so in a thread-safe way. We make sure that we're not going to corrupt shared state, and we work with hosts like SQL Server to make sure that they don't do things to your code while it's running that would compromise shared state. With that said, classes like the list of T class I gave an example of earlier, by default, we don't make those thread safe in the sense that if you publish a pointer to an object and then you share it across your application, It's not guaranteed to work correctly. In fact, it's probably not going to. There are a few cases like the thread class that we make this guarantee. We do that because the thread class, we believe, will primarily be accessed in concurrent scenarios. But for the most part, if we were to go and add locks around all of the methods in the framework, that would result in a pretty poor performance degradation. It's an optimization that we take, and if you share these objects, it's up to you to actually go ahead and lock these things. And of course, if you're developing a reusable library for your own company, this is best practices. It's worked for us thus far. This is sort of the guidance that we give to people when they're developing their own libraries. So you may have heard of some of these things in Jan's talk. These are some of the challenges you can run into once you start using locks. So for example, a deadlock situation. Most people are familiar with this. It's when two items are acquiring, or two concurrent workers are acquiring two locks in the reverse order. And this diagram here kind of shows thread 1 gets in, acquires lock A. At that point, thread 2 runs and acquires lock B. And then thread A resumes and tries to get B, but can't because 2 already has it. Now, this is pretty simple to determine. Your program will completely lock up unless you have some sort of deadlock detection. And the solution is usually using something called ordering or lock hierarchies, where if anybody has to hold lock A and B simultaneously, they have to access them in a certain order. For example, always acquire lock A before lock B. There's a thing called a priority inversion. Now, this is a situation where you have a lower priority thread and a higher priority thread. They both share access to the same lock. Now, if the lower priority thread holds that lock and the higher priority thread wants to run, it won't be able to. It's going to get blocked when it tries to acquire the lock. There are some even worse situations that can occur. For example, if the lower priority thread's executing and then a medium priority thread is available to run, the OS is going to give that the priority over the lower one. It will run, and then the lower priority thread will never be able to wake up and release the lock. So this has the effect of actually starving the highest priority thread from making any progress whatsoever. And this is solved in part by using a thing called boost and Windows starvation policies. If you went to the Windows internals pre-con session, they had a great discussion around anti-starvation policies that Windows employs. There's a thing called the lock convoy. So ideally, once a thread was done using a lock, the next guy in line waiting for that lock would get a chance to run. But unfortunately, due to time slicing and the amount of time that a quantum consumes, like one thread may own the lock, release it, but it still continues to run because it hasn't expended its quantum, which has the effect of other threads just sitting there waiting to acquire the lock. And if you have a very contentious lock, this can be a really horrible hit to the scalability of your program, because you could have all these threads coming in simultaneously trying to acquire the lock and all just waiting in line for a very long time. Boost is another example, or the solution to this as well. So you can imagine if thread 1 released its lock, you would boost the next thread in line. That is, give it the quantum and maybe slightly boost its priority so that it can make forward progress. Jan mentioned this as well, but it's important to understand that some items are shared across app domains. So for example, system type instances are shared across app domains. Strings can be interned across app domains. So if you lock on the string foo in app domain A and do the same thing in app domain B, they're both locking on the same instance, or they can be. This can lead to accidental deadlocks with code running in completely separate app domains, which can be pretty surprising. And furthermore, if an app domain gets unloaded, depending on the circumstance, it may not actually release the lock. So it may end up orphaning a lock and then leading to, again, another deadlock, which is difficult to track down because you actually didn't share this. You didn't share the lock among the different app domains. It just happened underneath you. So there's also scalability challenges. It's always a trade-off determining what granularity to lock or to take locks. So if you lock too coarsely, obviously if it's a high throughput section of code, then you're forcing, again, it's sort of the lock convoy problem. A lot of a lot of workers are trying to acquire the same lock at the same time and getting blocked and having to wait. But conversely, a lock that's too fine has a performance overhead because if the code you execute within the lock is very small in terms of cost, the lock acquisition and release could actually dominate the cost of computation. And furthermore, it can lead to deadlocks if you're taking things out of order again. So let's touch on atomicity for just a brief moment. There's actually a challenge here when you're writing, you know how I said, just write a try catch or a try finally block. So there are some situations where it's not so simple. So the goal, again, is to make sure that anybody who locks, who follows the locking protocol, never sees broken invariants. So how do you do this? Well, you patch up broken invariants upon failure, if you can. But achieving this 100% of the time is actually a little bit trickier than you might imagine, because sophisticated hosts like SQL Server can inject thread abort exceptions. This can happen when you've mutated data structures. You'll have to catch the exception and deal with it appropriately. However, these things are not processed if you're in a constrained execution region, catch or a finally block. So this saves you, okay? So if you're executing a finally block and a thread abort occurs, your finally block will actually execute to completion. Static constructors are another example of where we don't process thread aborts. We actually delay them until you exit that block of code. And if you want to learn a little more about these constructs, I highly recommend going to the Windows reliability talk, which I believe is on Thursday. They'll talk a lot about constrained execution regions, safe handles, things like that. New features in CLR 2.0. But you shouldn't really panic, because the CLR actually, this is assuming you're using one of the locks we provide, not something that you've written yourself, which we'll take a look at in a moment. But if you're under a lock, we actually work with the host to make sure that he doesn't go and inject a thread abort when it would actually compromise shared state. So if you see a thread abort exception, for example, you can assume that your finally blocks will run, your finalizers will run. The only scenario where you really need to worry is if you've actually mutated cross-process states. Remember in the first slide here, we talked about sharing things by using memory mapped I/O. We talked about kernel objects. If you're doing any of that sophisticated unmanaged interop, then you're definitely going to want to use safe handles, take a look at that feature, and go to Brian's talk on Thursday, the reliability talk. So there are some best practices you can follow when running code in parallel as well. So you have, it may be daunting to look at the choice of parallel APIs you can use, but it's pretty simple to make your choice. So the first thing is you need to determine whether you're doing explicit threading or whether you have sort of a lightweight asynchronous task. The difference is explicit threading is usually used in cases where either you're doing a really sophisticated thing where you're managing your own pool of threads. You may actually be constructing two threads that have a special relationship with one another, like a parent and a child. Or you may be doing something like a producer-consumer. In these scenarios, you want to use explicit threading because you can actually manage the relationships, you can manage the lifetime of the thread. You can be intelligent about how you're constructing threads. But at the same time, if all you want to do is fire off a quick asynchronous task that's going to execute on a separate thread, thread pool is your friend. There's queue user work item, takes a delegate, and it runs it on a thread pool. And the thread pool actually manages making sure that there's the correct amount of threads based on the architecture you're executing on and based on the amount of work that's coming in. So the workload of the thread pool is automatically taken into account when the thread pool either grows or shrinks the number of threads that it uses. Now there's actually another API that we've introduced in 2.0 called background worker. Now the problem with UI threads, as we'll see a little bit later, is that if you want to touch any of the components on the UI thread, you actually have to do that on the UI thread. So you can't do that from the thread pool. So what you want to use is the background worker class. And when you use that, the background worker handles the transition from executing on the thread pool and then signaling completion back on your UI thread so that you can process it in a natural way, such as setting flags on controls, updating status of controls, and things like that. one thing that I didn't mention is a lot of APIs have asynchronous versions. And these usually are optimized for the scenario. So for example, the file stream class has a begin read, a begin write, end read, end write functions. So these follow the asynchronous programming model, otherwise known as the APM. But the nice thing about that is file stream can be intelligent because it knows it's doing file work. So it can take advantage of I/O completion ports on Windows, which is critical to achieving high scalability in server scenarios. So roughly speaking, the order of preference is use the async API if it's available on the class you're working with. If not, then you have to decide, am I using a UI? If so, use background worker. Otherwise, use thread pool directly. Now, asynchronous APIs, these sort of lightweight tasks, often you need to figure out when it's completed. So this is called rendezvousing. So you're going to schedule some work to occur on the thread pool, and you want to be notified when it's done executing. There's actually too many ways to do this in the framework, if you ask me. So there's 4 ways. You can supply a delegate, and the delegate gets invoked by the asynchronous API whenever the task is complete. You can use so calling the begin operation function, according to the APM, will return an iasync result. And that has an isComplete Boolean flag that you can just poll if you'd like. And this is often useful if you suspect that by the time you reach the code that checks isComplete, that the work will have been completed. It avoids having to go through, for example, a delegate. It avoids having to go through a wait handle, which is the third option here. Wait handle enables you to wait until somebody signals the wait handle. So if you call wait1 on the wait handle that's attached to that iasync result, it's going to block until the operation completes. Lastly, you can just call the end function. This actually automatically checks the status, and if it hasn't completed, it will block using the wait handle. However, you do need to make sure that you always call the end function because it can release resources, and it's always better just to follow the programming model. Some iasync results may actually not hold on to resources, but most of them have to at least allocate the wait handle. So if you're not calling end xxx, it's not going to actually dispose of the wait handle in any other state that may be contained within it. So that's it for the shared memory section. Let's move on to taking a look at lock implementation. So here's a simple spin lock. You might want to go implement this yourself. It looks simple, it sounds simple, it seems very simple on the external. So what we have here is a class that has an integer called state. State can hold one of 2 values. 0, which means the lock is available. 1, which means the lock is currently held. When somebody enters the spin lock or acquires it, what we do is we go into a while loop, and we call the interlock compare exchange function. What this function does is it takes a by ref, a reference, to a memory location. In this case, the state field. It then takes a value that it wants to put into that memory location. And the third argument is actually the value it expects to be in the memory location. And if the memory location doesn't contain that value, it won't actually touch it. It won't swap it. And then it returns the old value that it saw there. So we loop around until we saw 0. If we saw 0, then we did put 1 there, and it means we now hold the lock. And then the function just exits. And then we have the exit method itself, which simply sets state equal to 0. So this means that we're done using the lock, we can release it. So let's take a look at how our spin lock performs. So here's our simple spin lock. This is exactly what was on the slide there. If I pull up the program here, take a look at what we're going to do. So we're going to spawn a bunch of threads, thread count, which is currently equal to 10. We're going to loop around, and we're going to construct each one of those. And we're passing the worker method here. We'll take a look at that in a minute. So each thread is going to run concurrently, and it's going to run this method. We actually have this stat class. This is actually just so I can track some statistics in the program to show some nice output at the end, just a summary of how the demo went. And then we start it up. and we wait for somebody to press a key. So here's the worker function. Worker just spins around until exit has been set to true, which gets set to true whenever I press the key. This is to make sure that all the threads shut down in a controlled fashion. These stopwatches are pretty much irrelevant. Again, it's for gathering statistics. But the real meat of this is right here. So we're going to acquire the spin lock. And then we're going to do something inside, like loop around a bit. And then we're going to release it in the finally block. So let's take a look at how this actually this fares. So go in here, we'll run spin lock. So I created 10 threads. And this is actually printing out the thread ID of the thread that's successfully acquiring and then releasing the spin lock. You notice, even though there's 10 threads, only thread 3 is running. And at the end, I hit enter and thread 3 exits, and then the rest of the threads right here got to run. And then I have a summary here. And this summary table just shows me the different threads that were constructed, the amount of times that they successfully executed. So thread 3 ran 250 times, while the rest of them only ran once. The total percentage of time executing, 96% for thread 3, 0.39 for the rest. Wait time, well, thread 3 didn't have to wait at all, but the rest had to wait quite a long time. So as you can see, this luck isn't very fair. In fact, it's very unfair. And the reason why is if you look at this, it's, first of all, compare exchange. It does some trickery with the hardware to ensure that it's the only thread that's accessing that memory location. So this could involve locking the bus. It could involve doing some cache coherency type of stuff. So this is actually the caches we're talking at hardware level now. The hardware makes sure that only one person can do a compare exchange simultaneously. So it's pretty costly. And all we're doing is looping and looping and looping, trying to do that. So once the code actually has the spin lock, what does it do? Well, it just does something that's going to consume CPU. It has no I/O calls in there whatsoever. So this is going to probably complete very quickly. In fact, it will be able to complete this, run to here, loop around to the top, and keep going without even having to release its time slice. It can all happen within one quantum. So only one thread will ever execute here. So let's take a look at how we can actually improve the spin lock. First of all, this is extremely wasteful on hyper-threaded machines. So Intel provides, you heard Jan talk about multi-core. I'm not sure whether he told you about hyper-threading, but this is a technique of actually having multiple hardware threads on a single processor. They share the same execution units, but they have their own set of registers. And it's efficient because one thread can give access to the other thread to run access to the execution units without having to do an OS context switch that saves the registers in some other place. So it's very efficient. But unfortunately, one thread, hardware thread, may be spinning and trying to acquire that lock, while the other hardware thread already has that lock. All it needs is somebody to give it some time to make forward progress. So Intel has this instruction. What I didn't mention is hyperthreading is actually an Intel-only feature. AMD has not released hardware that does hyperthreading or an equivalent, although they do multi-core as well. So this spin weight here is necessary to play nicely with hyperthreaded machines. So again, this is something you probably wouldn't think about if you were just writing a spin lock, but it can significantly improve performance. What it does is it emits a yield or pause instruction based on which architecture it's running on, which basically tells the processor, hey, you might want to let the other hardware thread run if it's ready to. Now, unfortunately, spin locks are supposed to be quick. I mean, ideally, they'd only loop around a couple times, and they'd acquire the lock and move on. But if we're developing a reusable spin lock, that may not be the case. So we may want to fall back to a more coarser-grained waiting mechanism in the case that the lock is not ready within a certain period of time. So the way we might do that is using an auto reset event. Set to false initially. And what's going to happen here is we need to keep track of how many times we spun around. So we can have a try count equals 0. But we also need to track whether we exit the while loop as a result of successfully acquiring the lock or because we exceeded a try count. So we'll want a taken equals false. And then we have to change our logic around a little bit here. So we want to change this. And then we want to say try count plus plus is less than, say, 10, for example. So what we're saying here is we're going to try 10 times, and if it doesn't succeed, we're going to fall back to the wait handle. And this actually has to be a manual. But it gets a little more complex because you really need to spin around until it's not taken. So here we need to say if we didn't take it, we need to wait. And then, of course, down here we need to signal. So we set. So this is so that another thread releasing the lock wakes up another thread waiting for the lock. But then, of course, there's sophisticated hosts like SQL Server. Remember I said earlier that SQL Server knows not to abort individual threads. When doing so could compromise the app domain. So what does that mean? It means that if there's one piece of code running that holds the lock and another one that wants to get at the lock, if this guy over here that already has the lock gets aborted, he may result in a deadlock because he may not release the lock correctly. So we need to play nicely with that too. And the way you do that is to say thread begin critical region. Down here we need to say thread end critical region. And the point is here that this builds up and becomes very complex very quickly. So let me, I'll pull up some pre-cooked code here because I'm not going to type all of this out. Another optimization, if you're on a single processor machine, you may want to skip the spin count entirely and just yield and let the other threads get access to the processor. So we detect that using the environment.processorCount property. And then down here we say if it's a single processor, we check once, we try compare exchange once. And if that doesn't succeed, we fall down here eventually and just wait on the wait handle. And then this is pretty similar to the code that I just executed. But let's take a look and see what the results of running the new spin lock are. So it succeeded. So ideally what you want to see is a very fair lock where every thread gets nearly identical amount of time inside of the lock. We'll run this. And you probably can't read that. At least I can't. But if we stop it, what you're going to see is that, first of all, you see a bunch of different numbers here. We still have this situation where a single thread can loop around and reacquire the lock, but eventually it will give it up. Now, if you wanted to, you could yield to other threads that were available to run explicitly. But that would be sort of a user program decision, not the general purpose spin lock. But the really, really nice thing is that if you look at the summary of which threads ran, how many times, and for what percentage of the total time of execution, you see they're all hovering around 10%. They all ran roughly 440 times, give or take. They all waited roughly the same amount of time and held. So the summary is, it's very difficult to get right. But when you get it right, the effects are very noticeable. So again, just to reiterate some of the points, most of you should not even think about writing your own spin lock, or any type of lock for that matter. If you need a lock that we don't provide, I want to hear about it. Then we can look at writing it for you and maintaining it, because most of you should be maintaining user programs, applications. And having to maintain a lock that many other people are going to be using is just problematic. It's very easy to get wrong, and you should just avoid it if possible. And the original attempt was pretty poor. I mean, it's the intuitive thing to try first, but it's a pretty poor attempt because it holds the bus, it starves other threads of forward progress, and besides, you don't want to spin on a single processor machine. And then again, we work with the hosts to make sure that they don't do anything that would result in inadvertent deadlocks. And one topic we didn't even discuss is affinity and reentrancy. So our monitors ensure that if you try to reacquire a lock that is already held by the thread, we just let you through. Otherwise, it might result in a deadlock if we actually blocked waiting for the same thread to release the lock. Alternatively, you could imagine throwing an exception saying, oh, we don't support recursion, but we actually do support recursion. Once you decide to support recursion, you need to track which thread currently owns the lock, which in the spin lock example might involve swapping instead of 0 and 1, 0 with the thread ID. And then the logic gets very complex very quickly. So memory models. We'll sort of touch on some of the interesting problems that can occur without a memory model there to save you. And then we'll see what our specific memory models guarantee for your code. So if you look at this example, you should be able to convince yourself that it works properly. So we have, this is a singleton, a pretty well-known pattern. And we're using something called the double-check block to ensure that we're guaranteeing that only a single instance will ever be created. Now, you could do this without locks, but you're running into the risk that multiple objects might get constructed simultaneously if there's multiple threads calling at almost identical times. So you see this class actually has two fields. It has a state, which is a string, and a Boolean initialized. And we sort of have the invariant that if somebody can see an instance of foo, then state is non-null, and initialize will be true. So you see the instance getter there, the property. First, it checks if instance is null. It does so without a lock, because taking a lock incurs some expense. And once the first one has been constructed, you'll never have to fall into the logic underneath that if statement. So it's much quicker just to check it without taking the lock. But if the instance is null, then we need to lock on the instance. And then we need to say, again, double check, is instance null? Because another thread could have gotten in there between the if instance is null and the lock statement. If it's still null, then we go ahead and construct a new instance. So you could imagine that the JIT might turn it into code that looks something like this. So we say we allocate a temporary structure, we say gcalloc type of foo, then we set state and then initialize in the order that it appears in the program. Then we publish the pointer to the new instance. But what happens if it turns into something like this? So we're setting the instance field directly using the gcalloc method. So first of all, immediately, somebody is able to see that pointer before you've initialized any of its state. Now the CLR makes sure that this is going to be initialized in the sense that it's zeroed out. It's not going to be some memory that was hanging around already. But then we go ahead and set initialize to 1 and state to I'm happy. But notice it's in the reverse order. So thread 2 could see, if another thread was calling into this and looking at the instance, it could see initialize set to 0, or it could see initialize equal to 1, but state is null, which means it's not actually initialized. So we'll see whether this is possible in just a moment. But a little background first. So it might be strange to think about the fact that things might occur in a different order that you actually wrote your program in. But compilers, like the JIT compiler and the CLR, processors, they want to execute reads and writes out of order for performance. So this code right here shows an example where the first example on the left sets y equal to 1, then it sets x equal to 1, then it sets y equal to 2. Well, it might actually try to optimize that. And it says, well, if I can make the second write to y occur before the write to x, then I have two writes to the same location right up against each other. Well, I can make an optimization and delete the first one, because nobody will ever see the first write of 1. So this has the effect of actually reordering them and actually deleting one of the writes. So what we say is the write of X passed the write to Y. It moved later in time. And JIT compilers can do this. It's called code motion. It can happen in sort of subtle ways where CPUs actually execute instructions in a pipeline fashion. They can do predictive execution, like if you're doing a write that's going to take, there's some latency involved with it, they may start executing ahead in the instruction stream. And there's a thing called cache coherency. So modern CPUs use cache hierarchies to make memory accesses efficient. But writes by one processor, so each processor could have its own cache, right? So one processor can write, it'll go to the cache. But then the cache needs to be flushed to main memory for another processor to observe the effects of that write. This is called cache coherency. But you can imagine problems where writes get delayed, maybe the caches get flushed in different orders. A read could actually move earlier in time, for example, due to locality. So locality is when two things are in the same vicinity of memory. So a read of one actually pulls in an entire cache line into its cache, which could include the other value. So this might sound scary, but it shouldn't be, because we actually have memory models on the CLR to make most of this transparent to you. The only time that you would ever even notice something like this is if you're trying to do clever programming like the double-check locking, where you're explicitly not taking locks when you're accessing protected memory. Remember, Jan said, just lock when you're accessing shared memory. It makes things much easier. You don't have to worry about things at this level of detail. So to sort of get some terminology out there so we can discuss memory models and what guarantees we make, there's three types, roughly, of controlling reordering. And this is the terminology we use in our memory model documentation. So load acquire means that the load isn't going to move after future instructions. So future reads and writes are going to happen after this load statement. And actually, the diagrams on the bottom might help to visualize this. So this is the program stream. Things that are higher in the stack are earlier in the program stream. The thing in the middle is the instruction we're talking about. And the thing on the bottom is things that occur afterwards. So the first one on the left is default load and store, where things can actually get swapped. So things can move before and after it. And then the next is the load acquire, which I just mentioned, where previous instructions can move after the load acquire, but nothing can move before it. Store release is sort of the converse. So it means that previous instructions are not allowed to move past the store release, but instructions can move before it. And then there's a memory fence, otherwise known as a barrier, which means that nothing can move with respect to the barrier. So obviously, the strongest memory model is one where nothing executes out of order. Everything executes as you wrote your program. The problem with this is it limits the ability of the processor to execute efficiently. So obviously, the reason why JIT compilers and processors perform out-of-order reads and writes is for performance. It's not because they like to make your programs incorrect. It's because they're actually trying to make your code run faster. And if you go with a sequential or program order memory model, it severely constrains the ability for them to do that. So we don't implement the strongest model, but we do implement something fairly close. So we guarantee that lock acquisitions and releases are fences. So this means is anything inside of a lock statement can't get hoisted above or below it. It all occurs within your lock statement. Again, another reason to use locks. We also guarantee that volatile loads and stores have acquire and release semantics, respectively. So volatile loads and stores aren't going to get reordered. So this is why you might want to use the volatile statement. We'll see in just a moment where precisely that can be used. In V2O, we actually have extended this, primarily because we're executing on IA64. This is the 64-bit Itanium Intel architecture, which has a lot of flexibility in the way that instructions can get reordered. And by default, it will reorder both reads and writes quite a bit, whereas previous architectures like x86 and IA32 would actually not. So this is the reason why some of you might read on the internet, double-check locking is broken, it doesn't work on the CLR. It actually does, and we guarantee it as of 2.0. It probably worked beforehand because the processor you were executing on wasn't reordering things, but it wasn't guaranteed. Now we guarantee it, and the way we do that is by making sure that all stores have release semantics. So when you publish the pointer to the newly constructed instance in the double-check locking, at that point, the previous reads must have been visible. So it's guaranteed that somebody else isn't going to see it out of order. So the summary is, we've done a lot of work to make the simple things work, the things you'd expect to work. But if you step outside of the bounds of the memory model, using locks, for example, then it just complicates your life tremendously. So some of you might be familiar with both the volatile keyword and the thread.memory barrier API. Given that we've already covered cases where things cannot occur out of order, you might wonder why they're still necessary. But there's two primary cases where it's necessary. So notice I didn't say that we guarantee that reads are load acquire semantics. So this means reads can still get reordered on you. Using volatile can fix that problem. And there's another subtle case where if you're doing a store release followed by a load acquire, well, the semantics of those still mean that they can get swapped around. So a memory barrier goes in between the two to make sure that they're not able to get reordered. Very subtle. It's probably the case that you will never have to use this API, which is a good thing. So for example, to take a look at this, an example where volatile might come in handy, this code snippet below, there's two static variables, an A and a B. Thread A is looping. What it does is it reads A and then B. And thread 2 is actually looping and incrementing them. It increments B first, then A. So B should always be greater than or equal to A. You should be able to convince yourself of this. In the memory model, you would think guarantees that somebody can't see those things out of order. But in actuality, we still permit loads to get reordered. So this thread 1 code here, if thread 1 actually read in the value of B first, maybe it read something that was close to it. So B had locality with some other memory location that was read before A. It could still be in the cache. So we actually, in that situation, unless A or B were marked volatile, you could actually observe writes out of order. But you're not actually observing them out of order. You're executing the reads out of order. And we permit that unless you mark it with volatile. So that was pretty deep. And unfortunately, the next section is also deep. But hopefully that's why you're here. So we're going to take a look at GUIs and COM architecture on Windows. So way back in the good old Win16 days, we didn't have these fancy things called threads. Right? So we used the message queue so that an application running on a GUI could simply post messages back to itself. And then there was a main message loop that would pick up those messages and do something with them. It would dispatch them. You would see the effects of the UI. You might use it for dispatching program logic, for example. And then threads come along, Win32. And now there's a sort of fundamental design choice that needs to be made. Do we allow multiple threads to access the UI concurrently? Well, that's pretty difficult to implement. And you know what? Most machines are single processors anyways, and this whole threading thing, it may not catch on. Probably not that naive. I wasn't on the team that decided this, but you know. So the other direction is, well, we'll require everybody to communicate with that single UI thread. We'll have only one UI thread that owns these bits of the UI. Any other threads doing program logic that need to schedule work that executes on the UI thread have to do so explicitly. How do they do that? Well, you see number 1 here in the flow. They either post or send a message. What this does is just in-queues a message. And then the GUI thread has this message pump where it's looking, is there something to process in the queue? If so, then go ahead and dispatch it. And it dispatches this on the GUI thread, which is not affinitized to a processor, which somebody might mistakenly think after seeing the word affinitized there. What I mean there is that the GUI thread owns the UI, so it's affinitized to the UI. No other threads can legally access it. So this is all great. Completely separate topic here, COM. You might think they're completely unrelated, but we'll see in a second how they have this fundamental tie at the lowest level of the architecture. So COM has this notion of apartments. So writing threading code is pretty difficult, which most of you are probably thinking right now after seeing Jan and my talks. I mean, it's certainly more difficult than writing sequential code. So COM has this notion of apartments that basically enables programmers to write components as though they're running sequentially. So a single threaded apartment guarantees that any components created within that apartment, now these are COM components, not CLR objects. The protocol is that only that thread within that apartment, there's only one thread within an STA, that thread is the only thread that can touch those components. Then you have the multi-threaded apartment, which is effectively free threading. There's either 0 or 1 in a process, and it can contain any number of threads. So these threads can be concurrently accessing objects within the apartment. And then there's this neutral apartment, where there's no threads inside of it. Any threads can call into the neutral apartment and access components without having to worry about transitioning, which I haven't mentioned yet. So you might consider the scenario where an MTA, a component on an MTA, needs to execute some code or touch a component on the STA. So as we've already established, a thread in an MTA cannot touch a component in an STA. So what is it to do? Well, what it does is it actually has to transition onto the STA thread. And how does it do this? You may have guessed it thus far. It uses a GUI thread. So an STA actually uses a message pump. And MTAs that want to schedule work onto the STA do the same thing that somebody wanting to schedule work onto a GUI thread would do. They post or send a message. So each STA obviously needs to be checking to make sure that it has new items in the queue, and when it does, it needs to dispatch them. And if it's not, then the STA isn't going to be responsive. In the same way that a GUI thread will lock up, you know, the nice little not responding in the title bar, very helpful, right? When that happens, it means basically the STA or the GUI thread has locked up and it's not processing incoming messages, including your clicks, your mouse moves, and things like that. The same thing can happen with an STA thread because it's using the message pump. If it's not checking for incoming messages, then it's going to get stalled. So the nice thing is that most of this is abstracted away. So if you're just using COM proxies automatically do the post messages for you. It pumps waiting for a reply, and it marshals the response from the STA back onto the MTA thread. So a simple method call on a COM component in an STA, it just looks like a method call. Underneath the covers, all of the gunk that works with message queues and all that, it's abstracted away from you. So the way that pumping works is the STA is going to look. It's going to say, is there a new message in the queue? And it has to do this while it's actually executing other code on the STA. So it's probably running code for one of the components in the STA, and it needs to take time out of its busy schedule to check the queue, and if there's something there, it needs to dispatch the message. Now, this is a little tough to get your head around, but what it means is that you can have component executing code, and then at some arbitrary point during its execution, it looks to see if there's a message in the queue. If there is, it will take that and execute it on its thread. And this has the effect of taking multiple logical call stacks and mixing them in on the same physical call stack. This is called reentrancy. And as we'll see in just a minute, reentrancy is kind of at odds with pumping. You know, you need to pump to ensure that the STA is lively, that it's processing messages quickly, you know, that MTAs aren't sitting there waiting for the STA to pump. But at the same time, reentrancy can cause some pretty subtle bugs to occur. As a matter of fact, let's take a look at one of those bugs right now. So we'll look at this program here. What I didn't tell you is that there's a service component class that if you derive from it, it's a CLR object, or it's a CLR type. If you derive from it, instances of that class actually abide by all of the COM apartment rules. So if it's created within an STA, the CLR will handle the transition from an MTA thread onto the STA. So we're going to use that to sort of simulate something that could go wrong in a COM interrupt scenario. So what we do first, we construct this new instance of some shared data. We'll look at what that is in just a moment. Then we go ahead, this loop here creates 10 new components. So let me take a look. Five my components inside of an STA. Now, how do I know it's an STA? Notice this little thing on the entry point here. This tells the CLR to run the primary thread for this application inside of a single threaded apartment. You'll see this on lots of projects like WinForms, Avalon, and it's there to make sure that the primary GUI thread is running inside of an STA context. It's also necessary in COM interrupt scenarios to make sure that the COM components you're creating are actually inside of an apartment that they have been written to be compatible with. Remember, one of the benefits of using an STA is you can be completely ignorant about the various threading scenarios, threading concerns when you're writing a COM component. It makes life easy. So at this point, we have 5 components in an STA. Now what we're going to do is construct 5 threads. And what we're going to do is actually set the apartment here. Each one of those threads is going to be placed into the CLR's multi-threaded apartment. There's a couple interesting steps here. The effects are going to be pretty interesting. Each one calls do work on its respective component. So each thread has one component that it's accessing. And we start them up, and we just wait for them to complete. The coords class has 2 fields, x and y. So our function down here, which is, so inside of our class my component, derives from service component. Remember, service component plays by all of the rules that a COM component does. So inside of our do work function, we just print out some stuff to the console. We take a lock. Okay, remember, locking protects other people from seeing your broken invariants. We took the lock before we broke any invariants. We check to make sure the invariant holds. It should always be the case. And then we go ahead and increment x. So the invariant in this case is pretty silly, actually. All the invariant says is that both coordinates must be equal. It's a little unrealistic, but it's pretty simple to observe the effects of this. So within this body here, we go ahead and we do some file I/O before we've actually done the paired operation down here to increment the y variable. So we do a begin write. Remember, this is what I told you about before. So this is actually going to use I/O completion ports. It's going to work well on servers. So this is really the way you would probably write your file I/O. And then do some expensive work in here while that I/O operation is occurring. Make sure we wait until it's complete. Probably process its results, although we don't in this example. And then just before we exit, we make sure that the invariant's held. So that means that x is equal to y as we exit the function. So let's take a look at what running this So let's see what running this produces. So execute this. Oh, looks like it worked just fine, right? I mean, each do work function happened in a serialized fashion. So 1 ran and then exited. 2 ran and then exited. Now what happens, though, if there's some sort of STA message pumping that gets introduced? Well, how might that get introduced? Well, in this situation, we're taking so long in the loop that the I/O operation is probably running to completion before we call end write. But let's remove a couple zeros here so that this is less expensive. Compile that, and we'll take a look at what happens. Whoa, our invariant doesn't hold. And you'll notice something strange in this background window here. 5 of the components went in to do work, but none of them exited yet. So that's definitely not achieving serializability. And if you look at the stack trace, we get a few down here. It's been truncated, but it looks kind of strange. You know, it's coming from message.dispatch, sync process message. You know, a lot of stuff is happening under the hood to make this actually work. And sure enough, our invariants aren't holding. Now, why is that happening? Well, it turns out that if end write has to block, which would occur if the file I/O hasn't completed by the time we reach right here, it's going to run the message pump. The message pump's going to take anything in the queue and actually dispatch that. Dispatching that effectively has the effect of do work executing on multiple components. Each one is going to try taking the same lock. But remember I said earlier, on the CLR, we support recursion. So if the current thread already owns the lock, it just goes through. Unfortunately, we hold locks at the thread level. If all the components are running on the same thread, as is the case with an STA, each one of them is going to be trying to stamp its thread ID, which is the same, on the lock. So the bottom line is we simply let the code through here without achieving serialization. So that may be kind of scary to you, but it demonstrates some of the subtle bugs that can occur without you even thinking that it's a problem. And it can crop up in COM interrupt scenarios. And really the solution here is to use like a kernel object, like a mutex, or something more sophisticated. So let's jump back here. So the good news is that the CLR does a lot of this for you. As we saw, it does transitions. It pumps the STA whenever you block. It places your threads into an MTA by default. So this is probably what most programs would want unless you're running on an STA GUI thread, or unless you're hosting components, COM components, that have been written to be only compatible with STAs. You can override the default, of course, if you know what you're doing, by applying the STA or MTA thread attribute to the entry point of your program. And of course, setting the apartment state for explicit threads. We actually made a change in 2.0. Before, you could attempt to change the apartment state on a running thread through the thread class. And then if that didn't work, we would silently ignore the problem. We wouldn't report the error back to you. So now we require you to actually explicitly do this before you spin up the thread. So you may have constructed the new thread instance. Before you call start on it, you have to place it into whatever type of apartment you're interested in. And as I mentioned before, Visual Studio sticks a lot of these attributes on many projects. We saw this. So a somewhat related topic is finalization. So finalizers run on a single thread that the CLR owns. That's placed into an MTA. So remember the rules for accessing objects in an STA? So you can imagine pretty bad things happening if there's a lot of components in an STA that the finalizer has to access that are not pumping. If they're not pumping, the finalizer can just get stuck. It will sit there waiting for the first pump to occur on the STA thread. And if that never occurs, well, the finalizer is never going to see anything else later in the queue, which means that over time, resources leaks are going to build up, and hopefully at some point the STA will pump and let the finalizer go through its queue and drain the queue. There are scenarios that we've seen, for example, hosting classic ADO, which actually wants to run in an STA by default. It says it supports both, but there are actually cases where subtle brace conditions can cause ADO to fail. So most people actually place those into an MTA. And then on ASP.NET, the finalizer thread, or any client application for that matter, may be trying to finalize those ADO objects. And ADO, by default, the proxies that get created don't actually do any pumping. So this can be problematic for obvious reasons. If you go read Chris Broom's blog, I'm sure many of you are probably familiar with it. He writes book-length essays at times. He has one essay on this very topic. And lastly, there's resurrection danger. So resurrection is the case where you have become inaccessible. Your object is no longer accessible, and then gets placed into the finalizer queue. The problem is people that have been placed into the finalization queue with you, or objects, not people, can actually refer to your reference. And what can they do with that? They can actually publish that to other people. So they can set a static variable to refer to your object. And then that has the effect of resurrecting your object. It suddenly becomes visible to your entire program once again. Now, you can imagine if you got finalized first. So you've already gone, your object's been finalized, everything's good. Somebody behind you in the queue publishes a pointer to you. Well, that means other people can access you after you've gotten rid of your resources. Hopefully your code has been written in a manner to expect this and fail in a predictable manner. But the reverse is also true. Somebody can run before you and publish the pointer to your object before you get finalized. Now what that means is that your pointer is now available, and then the finalizer thread is going to run your finalizer. And at the same time that's happening, other people can be accessing your component. And this can lead to some really subtle race conditions. You might not think that your finalizer method has to be thread safe. And in general, it shouldn't be. But if you're using something like safe handle, this isn't a concern because safe handle's written all this hard code for you. But using, say you have an endpointer handle that you need to close, you can imagine somebody executing some function on your object before you get finalized, and loading up the endpointer on its stack, and then your finalizer running. Finalizer will go and close the handle, and your object's been finalized at that point. But the other code that's running will still have the endpointer on the stack, and it will just resume going along its merry old way, past the endpointer to a Win32 function or something. Now, one of two things can occur. Either that's an invalid endpointer, and Win32 will detect that, or maybe the handle has been recycled. So this leads to what's called a handle recycling attack, which can lead to some pretty nasty security bugs. That's why in 2.0 we have this safe handle class. It takes care of all of that for you. So the moral of the story here is resurrection can be useful in some circumstances when you want to pool objects, for example. But in most cases, you shouldn't do it to your own code. And you certainly shouldn't do it to other code that hasn't been written to expect it. So that's the content of the talk. The summary is, we try to make concurrency simple for you. I've shown you some not so simple things on concurrency. Jan showed you some, well, I won't say simple, but locking makes it possible, tractable to do concurrency. The hardcore architecture implementation details sometimes come in handy when you need to debug hard-to-detect bugs, for example. When you need to architect massively parallel applications, you probably need to know a lot of this. But most people can be very efficient writing concurrent code without knowing any of the topics in this talk. And remember, the future is a fun place to be. Go write concurrent code after you've made sure you don't block your UI thread, after you've made sure that you've done all of the algorithmic performance tunings that you need to do. And there are some other talks, too. So if you missed these first two talks, I highly recommend watching them on the DVD once you get it. And there's also two talks on Friday, both of which talk about future directions in concurrency. So the first one here is a Microsoft research talk. It talks about a lot of really interesting projects that we have going on in research that could become productized in the future. And then Herb Sutter is going to talk about some future directions in the C++ language that make it easier to write concurrent code using C# language. And then other related talks, while not directly concurrency. The first one is that rock-solid reliable apps talk I told you about that talks about safe handles. There's Raymond Chen talk, 5 things every Win32 developer should know, that talks about some of the things I mentioned here. And lastly, tomorrow, the Link talk. I'm sure all of you are planning to go to that anyway, so I don't need to pump it up that much. Some resources, various blogs that might be of interest to you. My book is actually coming out early next year, January or February next year. I talk about concurrency a bit. The topics I discuss are more broad, though. CLR, new things in the .NET framework for 2.0. This Patterns for Parallel Programming book is excellent. It has some really sort of cookbook patterns that enable you to, first of all, figure out where that hidden concurrency might be in your application and how to take advantage of it. This last book, while it's concurrent programming in Java, it's actually very, very pertaining to C#. A lot of the topics discussed there transfer very nicely over to C#. A lot of the constructs in Java are similar, and it talks about a lot of fundamental concepts that aren't specific to a technology. And that's it. Thank you. So we don't have a lot of time for Q&A, but if you want to step up to the mics, I'd be happy to answer a few questions, and we can, of course, talk afterwards if you want to.
Hi. Can you back up one slide?
Back up? Oh, sorry.
I've got a question about if you're running code in a hosted environment like ASP.NET.
Yes.
The C# lock keyword generates code, I guess, akin to monitor.lock and then try, and finally it monitor.exits. Is that safe in the presence of asynchronous exceptions like thread abort exceptions?
It is. So the CLR guarantees, so it works with hosts to make sure that once you've acquired a lock, the host knows not to interrupt the code. So assuming you've acquired the lock, the host isn't going to do a thread abort exception. However, what it can do is unload the entire app domain. So in this case, it's OK because you're locking on something that's local to the app domain. And although you'll still see a thread abort exception, the entire app domain is being unloaded. So bottom line is you don't need to worry about that situation.
Unless you do something like put your assembly in an app domain neutral space.
So if you're sharing a lock across app domains, I should actually talk to you offline because I'm not actually sure whether we guarantee that we'll never orphan a lock across app domains. But I'm sure we have to, otherwise we couldn't guarantee that your code wouldn't deadlock on you. So
thanks.
Hi. Sometimes we would like to run a lengthy operation and it stops the program execution while it runs, but do not stack the UI. For example, we have an ActiveX that has a method which takes a long time. We call it from a JavaScript. We don't want the script to continue running, but just wait. But we don't want to lock the UI. Today, we program mainly in C++ and use the Windows API, so we use message wait for multiple objects.
Yep.
Is there something smarter in the .NET to achieve this goal?
Message wait for multiple objects actually does pumping for you, so that's a good way to ensure that the GUI thread is actually processing messages from the queue. And actually, it really depends on the scenario, but any of the synchronization mechanisms, like wait handle, for example, when you block on a wait handle, will perform pumping for you. So if you're just using the synchronization primitives that we provide, it'll all happen for you under the covers.
Oh.
So you don't have to insert like a p invoke to message wait for multiple objects or anything like that. It just works.
Great.
Okay.
Yeah, I was wondering if you guys are looking at future versions of Visual Studio debugging tools to help debug multi-threaded issues.
Absolutely. If you go to the MSR talk, there's a tool called Racetrack, which helps you actually detect race conditions in your code, as well as deadlocks. Obviously, it's a research technology, but we understand that debugging concurrent applications isn't as easy as it should be. And so it's definitely something we're looking at in the future.
Cool, thanks.
Yep.
Suppose I want to do kind of an interesting feature in an ASP.NET application, or I want to allow a user to set off a long-running process, and in maybe a small corner of that, maybe it's a frame or something similar, I want to show like a little spinning globe to show that something's happening in the background, and when something changes, something in the frame will change. Is it safe to use a thread pool thread to run that long-running process, knowing that ASP.NET is also going to use those to serve as threads, or should I look at doing something like MSMQ?
So what I'm picturing is, so you have your client application, and so it sends off a request, which is going to take a long time, and
like
it
a
returns
report.
from the server, and it needs to poll to see if that request has completed.
Yeah, maybe the user's running like a query or a report, but we want to let them continue to use this kind of rich web application. So they get a little thing that says, yeah, your report's running. You can keep doing things. And then when that's finished, that'll maybe turn into a hot link that'll get them to the report or the query results or something like that.
Yes, I'm not particularly sure what the best way to do that is, because it involves a lot of synchronization between a web client and a server. So surely on the server you could use the thread pool to schedule this long-running task, and then I guess you could set a flag or something when it was done, and then the client has to keep polling to see if it's done, right?
Right, yeah.
But in terms of how specifically to implement that, I'm not quite sure. If you want to talk offline, I can probably find somebody that can help you.
Okay, thank you.
Okay.
Let's say you have a bunch of threads that are accessing shared state, say an integer. Some of them are reading, some of them are writing, and you don't lock it. Are there cases in which the assignment could be a partial assignment? Like I understand maybe a 64-bit integer and a 32-bit, you might just assign the high order instead of low order. So which kinds of variables are safe for that? Are references to .NET objects safe in that scenario?
References are safe because we guarantee that references are a pointer sized on whatever architecture you're running on. So 64-bit will be the right size, 32-bit. If you're writing code that has to be architecture neutral, and say you're flipping a 64-bit value, there's actually methods on the interlocked class that enable you to do that in an atomic way to make sure that partial updates aren't observed. But that's the only scenario. It's when you're using something that using a data structure or a size that's larger than the native pointer size on the machine architecture.
Okay, so value classes that would be bigger than 32 bits would also apply. Okay, cool.
I noticed you mentioned racetrack. And that's the
Yes.
second time that's come in a talk today. Is there any likelihood that that's going to be made available publicly? Because currently I believe it's internal use only.
So I actually don't know. I would definitely encourage you to go to the talk. I'm sure they'll address that very question. They may have some plans that I'm not privy to, but I know you're not able to download it today.
Okay.
Okay, thanks.
A while ago, I was surprised to discover that lock acquisition isn't always FIFO. How can I get that?
So you could simulate it using your own queue or something, but in the CLR we don't have like a lock that services in FIFO order.
Will
So
we ever have it?
What's that?
Will we ever have it?
Sure. Well, I mean, is that something that you would find useful?
Yeah, to avoid starvation.
For fairness, yeah. So that is a fairly common request. So I'm sure we'll look at it in the future. Unfortunately, I don't have any specific information around whether we'll implement a new lock or how we would do that. But it's definitely a feature that a lot of people ask for.
Okay.
Thanks.
In the asynchronous API, you have a limitation of up to 25 asynchronous calls per microprocessor. Are you aware of that? That is like a potential deadlock bringer.
I'm not sure.
Basically, you can do begin XXX.
Yep.
Okay, and you can do up to 25 of those at the same time. Okay, in a machine that has one microprocessor. And basically, what potentially could happen is that when the callback comes back, basically, you want to start the 26th begin something,
Sure.
and then you're screwed.
Yeah. I'm not sure. Maybe you want to talk offline.
Okay. All right.
I think I'm running out of time already. So thanks for coming, everybody.